Okay, so this is skateboard. Hopefully I won't get killed. I used to ride these one time. This is just a demonstration of Newton's third law. So I stand on the skateboard, hopefully without falling, right? And now I'm going to push on the wall that way, right? If I push on the wall that way, I go this way, right? That's how I get moving. I come over here and stand next to the wall, and then I push that way. And the harder I push, the faster I go. And so that shows that something is pushing on me. The wall is pushing back on me. If I push on the wall, as hard as I push on the wall, if I push on it just a little bit, I go a little bit. The harder I push, the faster I go. The wall is pushing on me as hard as I'm pushing on the wall. So this is Newton's third law. And you probably know Newton's third law, so pause and think about it for a second, and then see if you can tell me what it is. It's for every action, there's an equal and opposite reaction. This is the colloquial version, and it's pretty close to what Newton said. Maybe a better way to say it is forces come in equal and opposite pairs. You can't have just one force. If you apply one force, there's an opposite force. Another way to say it is the force due to object A on object B is equal to minus the force due to object B on object A. I should draw them as vectors, because the direction matters. These should just be dots, right? I'm just enumerating. These are all kind of saying the same thing. This is the most quantitative way to say it. If object A exerts a force on object B, then object B exerts a force that's equal to in size and opposite to in direction on object A. So, if this is my nose, right? And your fist punches my nose, then your fist exerts a force that way on my nose. F fist on nose is equal to minus F nose on fist. So if you punch me in the nose, please don't. We don't support violence. Maybe you could just gently punch me in the nose. The force your fist exerts on my nose is equal and opposite to the force the nose exerts on the fist. Forces come in equal and opposite pairs. So let's look at the forces on this cup and talk about what their equal and opposite pairs are. We already said that there's a force of gravity acting on the cup, and that's equal to the mass times the gravity, right? And it's acting in the downward direction. And then we said there's actually a force called the normal force, which is pushing upward on the cup. And in fact, that has to exactly balance the force of gravity, but these two are not an equal and opposite pair. This is the force due to the table on the cup, and the force of gravity is the force due to the earth on the cup. Right? And so we won't always label them this way. A normal force is the name we give to any force that acts on an object due to a neighboring surface, but we can also call it specifically, it's the force due to the table on the cup. Newton's third law would say that's equal to minus the force due to the cup on the table. And so if the table is pushing up on the cup, then the cup must be pushing down on the table. Similarly, this has to equal minus the force due to the cup on the earth. So if the earth is pulling down on the cup must be pulling up on the earth. So the gravity of the earth is reaching up and pulling down on the cup. The gravity of the cup is reaching down and pulling up on the earth. And those forces are equal and opposite. Similarly, the force due to the table on the cup pushing up on the cup, the table pushing up on the cup is equal to the force of the cup pushing down on the table. Notice equal and opposite pairs always act on different objects. This force acts on the cup, this force acts on the table. This force acts on the cup, this force acts on the earth. Right? If we're interested in what's happening to the cup, we're really only going to talk about the ones that are acting on the cup, the table on the cup or the earth on the cup. We're not necessarily interested in the equal and opposite pairs of those. They exist, but they may not be useful if the object that we're studying is the cup. Anytime we've got a particular object we're studying, we're only interested in the forces on that thing and not too worried about the other forces that are going on, even though we know that they're going on. So in this problem, a 10,000 kilogram rocket accelerates at 2 meters per second squared. And we want to know what the thrust force is on the rocket, right? And so if we look at our rocket, we can say, well, there's a thrust force that's pushing the rocket up. And we'll call it Ft for F thrust. Right? What other forces are acting on the rocket? Well, pause and think about that for a second. You would say, okay, there's the force of gravity that's pulling it downward. You might even correctly say, well, what about air resistance? Well, we're going to neglect air resistance, and we're going to say, look, these are the two forces. The thrust from the engines was pushing it upward, and gravity is pulling it downward. And the net effect is that it's accelerating upward at 2 meters per second squared. If we were to draw a free body diagram, we would represent our rocket as a dot. We would put the thrust force here, and we would put the force of gravity here. Again, you can call it the weight if you want to. And then we say, look, this acceleration is not a force. So in a free body diagram, the forces are acting on the object. The acceleration is what's happening. And I should always include that in my free body diagram, but not attach the object. This is just off to the side saying what it's doing. And the reason we put this in, well, one reason, is because this allows us to pick a coordinate system. And so when you pick a coordinate system, you should always choose one with an axis that has the acceleration along it. And this is kind of easy. The normal set of axes we might choose is a y going this way and an x going this way. And as long as we have one axis that's parallel to the acceleration, either along it or opposite it, then that's fine. I'll tell you why in a second. And so I would call this a complete free body diagram. It has all of my forces in it, and they're lined up along axes, and we'll find a situation where they're not in a little bit. And it's got the acceleration in a coordinate system. And so now my next step in this problem is to say, well, I'm going to solve Newton's second law. And so the key is I want to do it in the x direction and in the y direction. So I want to say the net force, which we'll go back to using the sum of, remember this one? The sum of the forces in the x direction equals the mass times the acceleration in the x direction. Just like we did with kinematics, we're splitting up the x and the y. And so this is Newton's law, Newton's second law for the x direction. And then we can write the sum of the forces in the y direction equals the mass times the acceleration in the y direction. Notice there are no forces in the x direction in this problem. And so what we're left with, we can just put a line through that and say nothing interesting is happening there. But for this one there are two forces acting in the x direction. And the point of this is that I can just read them off of here now. And so I can say, look, the force due to the thrust and the force due to gravity are the two forces that's acting. In my coordinate system, this one is positive and that one's negative, right? And my acceleration in the y direction is just this guy, and so that's just equal to ma. Now I can rearrange this, since what they're asking me for is the thrust force. They're asking me for this thing is equal to ma plus the force of gravity. But that's just equal to ma plus mg. Hopefully it's still on your screen. Now it is. All right. And so that says that the thrust force is equal to 10 to the 4th kilograms times 2 meters per second squared plus 10 to the 4th kilograms times 10 meters per second squared, because that's what gravity is, right? And so that's 20,000 plus 120,000, which is 1.2 times 10 to the 5th newtons. And so that's my answer. As a side note, you might look and say, well, how does this thrust actually push up on the rocket, right? And the answer is, when a rocket fires fuel out the back, as the fuel gets pushed out the back, it pushes back on the rocket using Newton's third law. So Newton's third law is what propels rockets. Anytime you see stuff getting fired out the back of a rocket, in order to get pushed out, it has to push back on the rocket, and that's how the rockets move forward. So this is a rubber band, and I just want you to notice that a rubber band is a nice demonstration of tension. You can get tension in a string or tension in a rope. So look at my top thumb up here, and you can see that the rubber band is pulling towards the other finger, right? It's pulling sort of down your screen on the top thumb, and it's pulling up on the bottom thumb, like that. It's pulling that way on the bottom thumb, and it's pulling that way. It's pulling in opposite directions on my two thumbs, right? In a sense, you can kind of think of a string or a rubber band or a rope as kind of an agent of Newton's third law, right? If these two thumbs were hooked on each other pulling, they would be pulling on each other with equal and opposite forces, because they're, whatever this thumb acts on this thumb, the other thumb acts the same way. And that's kind of what's going on when I have tension in a rope. It's pulling down on one and up on the other with equal and opposite forces. The magnitude of force is called the tension in the rope. And so if I cut this rope at any point, this rubber band at any point, one end, the top end would shoot towards that thumb, and the bottom end would shoot towards this thumb. So at any point, the tension is pulling in opposite directions. And so I'm going to do a few examples of tensions. Any agent of Newton's third law is, it's a stringy type thing. It's going to give a force that's a tension. And so let me just do a couple of examples of this. So the first one I'll say is so a 10 kilogram light hangs from a cable And so this has a mass equal to 10 kilograms. What's the tension in the cable, right? And so if we look at this guy, we know that he's got a force of gravity acting on him this way, which is mg, right, where m is 10 kilograms and g is 10 meters per second squared. Since the light is not, this might be an arena light or a chandelier or something like that, right, to be 10 kilograms, but it doesn't matter. Since it's not moving, since acceleration is 0, then we know there has to be a force balancing this one, and that's the tension. I'll just give it a T, right? And so if I were to draw a free body diagram over here, I would say, look, there's my bulb, here's the tension, here's the force of gravity. I would go along here and I'd say A equals 0, which means it doesn't matter, it doesn't have really a direction. I might pick a direction this way. Even though there's no acceleration, I might say, well, if there was going to be an acceleration, it would fall down probably. And so I might do that. And now I've got to pick a coordinate system. So here's y and x. And so now once I've drawn my free body diagram, I can solve this problem. I can say, well, look, the sum of the forces in the x direction equals m a sub x. That's applying Newton's second law in the x direction. Well, there is nothing going on in the x direction. All the forces are in the y. And so I can, just like last time, I can scratch that off. Sum of the forces in the y direction equals m a sub y. But that's just 0, right? Well, what are the forces? The forces are, that's a g, right? The forces are the tension and the force of gravity. And this guy's positive, and that guy's negative because he's pointing down. And so the tension equals the force of gravity, which is equal to mg, which is equal to 10 kilograms times 10 meters per second squared, and that's equal to 100 newtons. So there's a tension force pulling up on the bulb, and gravity's pulling down on the bulb or the light fixture or whatever it is. And so because of the way this is arranged, the tension balances the weight, and so the tension is equal to the weight, and that's just 100 newtons. So a speaker of mass 20 kilograms is supported by cables as shown, and so I'm going to show you here how it's supported. Here's my cable. This is a wall, and that's a ceiling, so wall, ceiling. And so I'm going to have a cable going this way and a cable going horizontally this way. And we'll call this T1 and this T2. Okay, and this is M equals 20 kilograms. Right. And so we want to know what are the tensions T1 and T2. Once again, I know it's not moving, A equals 0. And so I can draw a free body diagram for this thing. I can say, look, here's my object. I've got a tension going this way. That's T2. I've got a tension going this way. That's T1. I've got a force of gravity going this way, right? And I've got an acceleration equals 0. I can give it a fake direction downward. Right. And now I need to pick a coordinate system, but first I need to deal with the fact that I have one of these tensions that isn't along one of my axes. If I'm going to pick a coordinate system, I pick it based on my acceleration. It's going to look like this again. Right. Generally, if things aren't moving, you want to pick a coordinate system that's consistent with gravity or something like that, right? In the stationary case, if the thing's accelerating, if the object is accelerating, then you want to pick a coordinate system that has an axis along the direction of the acceleration. And so if for some reason this is accelerating at a weird angle, we would rotate our coordinate system. But here, we're just going to use our standard coordinate system. What we want to do with this is use Newton's second law. That's how we solve these problems. And Newton's second law looks like this. The sum of the forces in the x direction equal mass times the acceleration in the x direction. The sum of the forces in the y direction equals mass times the acceleration in the y direction. The problem is I have forces here that aren't, I didn't give you a piece of information, that that don't fit into either one of these. Right? This force here, T2, is not in the x direction, and it's not in the y direction. And so I have to use my vector skills and break this force up so that it's got an x component and a y component, and I'm going to replace the force with its components. And so I've chosen this as my coordinate system, and so I'm going to draw my coordinate system on top of my free body diagram. This is my x-axis, this is my y-axis, and then I'm going to draw a line down. I'm going to call this T2y, and I'm going to call this guy here T2x. If this angle is 45 degrees, that means that angle is 45 degrees. And so this angle is 45 degrees. And there's my T2. And so now I can say, look, T2x is equal to T2 cosine theta, where theta equals 45 degrees. And T2y is equal to T2 sine theta. Right. So now I can redraw this free body diagram, replacing T2 with T2x and T2y. Remember we said when we were working with vectors, you can always replace a vector as a sum of two other vectors that add up to it. And the reason we do this in these cases is because it allows us to use these formulas. It's the same reason we found the x and y components of projectiles' initial velocities, so we could use them to plug into the formulas for the x and y kinematic formulas. And so I'm going to erase the top part of this. We just have to remember that we want to calculate the tensions in the cables, and I'm going to redraw this free body diagram up here. I'm going to say, look, my free body diagram looks like this. It's got a tension going this way, and now up this way it's got a T2y, and then this way it's got a T2x, and then this way it's got a T1, and then this way it's got a force of gravity. My acceleration is still 0, and that's my coordinate system. This is what I would call a completed free body diagram. I have a coordinate system, an acceleration, and all of my forces are along one of the axes. If I ever have a force that's not along an axis, I have to break it down into components so that it'll be along the axis, because what I want to do with this is plug it into these formulas, and you can't take forces that aren't along an axis and plug them in. You can only plug in forces that are along an axis. And so if I do my sum of the forces in the x direction, I would get this. The sum of the forces in the x direction, so I'm going to do this one, right, is equal to m a sub x. That's just 0, right? And so this says T2x T1 equals 0. The two forces acting in the x direction are these guys. This one's in the plus x direction, but that one's in the minus x direction. And so this tells me that T2x equals T1, or T2 cosine theta equals T1. Right. I don't know what either one of those are, so I can't quite solve yet. But now I can do the sum of the forces in the y direction. Right? I can take this guy and write him here. And I can say, look, in the y direction I have T2y, and the force of gravity equals 0, right? The acceleration in the y direction is 0 because it's just hanging there, the speaker is. the T2y is positive, it points up. T2x, force of gravity is points in a downward direction. And so what I get is T2y equals the force of gravity, or T2 sine theta is equal to mass times gravity. Well, I know what theta is. Theta is 45 degrees. And so I can say, look, T2 is equal to mg over the sine of theta. And that's equal to 20 kilograms times 10 meters per second squared over sine of 45 degrees. Right. That's equal to 282 newtons. That's T2. Right. And so that's the first one we had to get. And now we need to get T1. T1 is equal to T2x, which is equal to T2 cosine theta, which is equal to 282 newtons times the cosine of 45 degrees, which is 200 newtons. And so my answer to the question, what are the tensions in the two cables? This one is 282 newtons, and this one is 200 newtons.